thank you, Tony. That's a good introduction. Thank you. Very, very kind introduction. So here, I'm very happy, to give this talk. So thanks again for inviting me. And so the purpose of the talk is to it's an overview of scientific machine learning from my perspective, personal perspective, and also mention some of our own contributions along the way to this. So we begin with this slide where we have, on the left side, you have no data and lots of physics, or all physics. And on the right side, you have lots of data and no physics. And on the left side, that's where you're gonna find purely physics-informed neural networks, Gaussian processes, even operator learning. In fact, you can do physics-informed operator learning. So, and then the way that we introduce the physics is typically there are two ways. One is a soft way where you modify the loss function or the score function, whatever it is that you're optimizing. You modify it with the physics. And the other way is the hard way where you embed the physical constraints directly into the algorithm. So there are these two different ways. And we'll talk about this. This is also where you find traditional scientific computation. So, in traditional scientific computation, you have no data. I mean, you have the entire specification of the physical model, and then you simulate the physics. You generate the data. On the other side, then you're going to have data-driven neural network Gaussian process operator learning, purely data-driven. So no physics. So here you need lots of data. In fact, and you're also going to find data-driven scientific computation. So, for instance, POD based on snapshots and so on and so forth. In the middle, there is some data and some physics. So here, I'm going to call these inverse problems. You can still use neural networks, Gaussian processes for system identification, parameter estimation, hidden fields prediction. I'll show you an example. So these are problems where you have some data and some physics. And when I say physics, I mean geometry also. I mean boundary conditions, right? So not just the PD. So you may know the PD, but you don't know the boundary conditions or the geometry of the problem. And then you have some data to make up for that ignorance of the physics. So I happen to think that neural networks, machine learning in general, is still quite unexplored in this part here, the inverse problems. And I think, there's a lot of potential for using machine learning in these kind of problems. Now, behind all of this, except for the extreme left side, we have the question, this question, is the physics in the data? Because you are, in fact, using the data to replace the physics. So here there is an important epistemological question, right? I mean, if you have an infinite amount of data, a thought experiment, if you have an infinite amount of data, can you derive all the physical laws of the universe? I mean, can you derive, quantum gravity, Can you derive a complete picture of the physics by using just data? All right. I happen to think that the answer is no, because we know in supervised learning, machine learning, we have these no free lunch theorems, where even if your algorithm is consistent or universally consistent, so consistent in every situation, meaning that if you have an infinite amount of data, you reach the optimal predictor, is still the rate of convergence can be arbitrarily slow, which means that you never have enough data. So yeah, if you had an infinite amount of data, you could do it, but you in fact have you don't have a guarantee of how much data you need. In fact, you could need an arbitrarily large amount of data, which you don't have. So this is an important question, but empirically we know that in many cases we can use the data to recover the physics, at least in simple problems or simple enough problems. So of course, I mean, the more complex the problem becomes, the more data you need. But you could still use the data to make up for the loss of physics or missing physics or incorrect physics or whatever. So that's the introduction slide. And then I would like to talk about each of these things as we go. So the first, obviously most well-known algorithm in scientific machine learning is the PINN. I think everybody here already knows about PINN or have heard about PINN. So this is a soft approach. There is a neural network, and the neural network, in fact, produces a prediction of the solution. So it's a coordinate neural network, like it's usually now referred to, or an implicit model, where the input is the physical coordinates, space and time, for instance, and the output is the solution at each point in the physical space. Now, using automatic differentiation, you can differentiate this output and you can compute a partial differential equation residue. So you could enforce this residue to be zero on a selected amount of selected points in the domain. I cannot use my pointer here, but you can see on the lower left side, you can see an example where you're going to have, of course, points along the initial condition, points along the boundary condition, lateral boundary conditions. You're going to have the axes, which are the collocation points, and you're going to have the orange dots, which could be data. In fact, you could still have data, or maybe you don't have any data. So in the purely physics-informed setting, there is no data. So yeah, so it's a soft approach because you're going to minimize the loss and you're going to encourage the neural network to satisfy the initial condition, boundary condition, and the PDE. It's not guaranteed to satisfy exactly, but if you have enough points and you have enough expressive network, big enough network, you can get very close. So that's why it's called a soft approach. And here's an example, of course, a very simple example. It's the viscous Burgers equation. And what we can see here is the solution of a PINN with 8 layers, 20 neurons each, 200 initial points, 100 boundary points, 20,000 collocation points. It's very fast. So we do 400 training iterations, and it's very fast to train this PINN. It's like on GPU, it's about a minute, okay? And so, of course, it's a very simple problem, but we can already see that the neural network is able to capture these very sharp transitions in the solution. And this is typically a basic benchmark, right, for most numerical methods for hyperbolic problems, transport problems. So the PINN does a very good job here. Now, it does not such a good job here. So this equation here, the Allen-Kahn, it is not a hyperbolic equation. It's a diffusion reaction equation. It is stiff, quote unquote, in the sense that it evolves. This discontinuity is very fast, and the fact is that the PINN cannot converge. If you look at the losses, and remember that the losses have different components. The loss has different components. There's a loss for initial points, for residue points, collocation points, boundary points. If you look at the components of the loss, you observe that the boundary loss is very small, so the boundary conditions are satisfied. The residue loss is small, meaning that the PDE is satisfied, because constant zero is a solution of the PD. But the initial loss is not satisfied. So this is the main failure mode, as it's called, of PINN, is that you have this complicated loss function with many components, and there can be an imbalance between these losses. Here, it's finding a solution of PDE, zero, but that's not the solution of the problem. So the question is, how can you fix that? So there's a big literature on this. One of the approaches is to use weights. So to weight the loss, and of course put different weights on different parts of the loss. So we contributed an algorithm in this setting, which is called self-adaptive physics-informed neural networks. This is already it was a few years ago, but it is well-cited paper. And with this approach, we can solve the Allen-Kahn equation. What happens is that we have some adaptive weights on each point, not on the entire loss function, but on each point of the domain. We can put weights, and those weights are adjusted during training. So they are, automatically adjusted during training. And so the network learns what are the critical parts of the solution. So for instance, here you can see that the yellow and green are the larger weights, and the purple is the small weights. And we can see that the weights are going to grow early, so near t equal to 0, and along where the gradients are, larger. So you have these structures forming. We can also see here, down here, so you can see my pointer, right? So you can see down here on the right, the lower right, you can see the average of the weights of the residue. These are the weights you're seeing on the upper left, and the average of the initial condition weights. And the initial condition weights, the green curve, they grow much faster, in fact, than the residue weights, because it's not capturing the initial condition. So it's going to put a lot of weight on the initial condition. But you see, the network learns by itself that that's what the trouble is. I mean, it is the basic idea. So if you now run the PINN, then you can see that it will now produce a good approximation to the solution. On the lower left, we have comparison with some other adaptive weighting methods. But so this is the self-adaptive PINN. The other thing you can do with PINN is you can do parameter estimation. And like I said, so it's an inverse problem. And like I said, these inverse problems, I believe there's still a lot of potential, okay, to explore. And what you're seeing here is the Burger's equation, where you're trying to estimate the viscosity. So you can treat the viscosity as a parameter in the loss function, along with the weights of the neural network. And then you can minimize the loss function, identify the parameters along with the neural network weights by minimizing the loss function. And you can use self-adaptive weights. You can use all the adaptivity procedures, right? So here you see an example where we try to identify the viscosity from noisy data on the solution. We have 10 runs. The parameters initialized in a wide interval. The true viscosity is 0.01 over pi, and you see that all the runs converge to the true value. After some oscillations, they eventually converge. On the right side, you see the loss, which is also converging. So this is a simple example, of course, but so I think this is a situation where you have some data and you have some physics. You're missing the missing physics here is, of course, you don't know the viscosity, okay? But you know Burger's equation. And in fact, you know the initial condition and you know the boundary conditions. You can make the problem harder. But here you're missing the viscosity. So you don't have the entire physics, but you have some data. So you can get it. Okay, so you can find, in fact, you can find the solution and the parameter simultaneously, right? Okay, the other approach, for soft physics informed is Gaussian processes. So in this slide, we have a very simple example. The idea is in fact, is similar to PINNs. You have the PDE, and if you have a linear PDE, you can differentiate. So you have a GP to approximate the solution. First of all, you have a GP to approximate the solution, just like you have a neural network to approximate the solution. But then you can differentiate this GP, just like you use automatic differentiation to differentiate the neural network. You can differentiate this GP through kernel differentiation. If the PDE is linear, you obtain another GP. So now you have two GPs, one for the solution and another for the residue of the PDE, in fact, for the PDE. So you can fit zeros to the residue GP, and you can fit initial condition data, boundary condition data to the first GP. And these GPs are, of course, jointly distributed. And then, obviously, you use the first GP or the posterior mean of the first GP as the approximation to the solution, and you can use also the standard deviation of the first GP posterior after conditioning on the data to have a measure of confidence or error. So in this particular case, we are seeing on the lower left the absolute difference between the exact solution of this simple advection equation and the GP posterior mean. So it's very low. It's very small. So it's very accurate. But obviously there is error. But if you look at the standard deviation on the right side, on the lower right, you're going to see that it's very correlated, extraordinarily, in fact, correlated with the error, the absolute difference. So in practice, you don't know the absolute difference, of course, but you have the GP posterior standard deviation. So this gives in this case, it's a very well-calibrated problem. You get a very well-calibrated standard deviation. And you can use this as a measure of confidence in your solution. Neural networks don't give you that, okay? But, with GPs you have. GPs have other challenges, which is, for instance, non-linear PDEs. You can solve them with neural networks very well, like the Burger's problem. So non-linear PDE. With GPs, you have a problem because you no longer have Gaussian processes. So now you have a more complicated inference problem. And you have, so essentially it becomes also less accurate. But there's also a problem with GPs of scalability if you have a lot of points. So a lot of residue points, a lot of initial points, because GPs have a computational complexity of n cube, where n is the number of points. But obviously there are scalable approximations and things you can do to alleviate that problem. Next slide is, again, the soft physics-informed Gaussian process. I'm going to show you here a different kind of uncertainty quantification. So the uncertainty here is going to be introduced by the discretization of the problem. So here is, so you have a wave equation, you're going to discretize it in space, and you're going to generate a system of ODEs, as it's often done. And then you are going to solve that system of ODEs using Gaussian process. Now here, we're going to actually use a Kalman filter to compute the posterior mean and standard deviation, which is an O of n in the number of time step discretization. So you're going to discretize in time the system of ODEs. You know, the GP would be n cubed in the number of time steps, but we use a Kalman filter and we get actually O of n. So this is one of the approaches to make the approach more scalable, okay? But here, of course, how fine the discretization is will affect the accuracy of the result. So, you know, if you do not discretize enough in space or in time, you're going to have a poor approximation. So there is an uncertainty coming from the discretization. So here I'm going to show you the solution from a coarse discretization to a fine discretization. So coarse on the upper left, fine on the lower right, and intermediates in between. So you're going to see that obviously the solution becomes very bad as time goes on. It starts well, but then it loses track as, you know, the time integration proceeds. And what you see is that the posterior mean is incorrect. The posterior mean is the red dashed, and the analytical is the black. Well, what you see here is that the posterior mean is incorrect, but the standard deviation points you to the fact that it's incorrect. On the lower right, the posterior standard deviation is 0, essentially. And the posterior standard deviation is in fact larger the more incorrect the solution is, I mean, the posterior mean is. So that's another example of well-calibrated Bayesian inference here, where, you know, your standard deviation can serve as an error estimator, okay, essentially. So with Gaussian process, you can also do inverse problems. So here the unknown parameter becomes a hyperparameter of your prior, along with kernel hyperparameters. And then you are going to use, to maximize the marginal likelihood, to set the kernel prior hyperparameters along with the parameters of the problem that you don't know. So here we are trying to find the velocity of the linear diffraction problem from sample noisy data. We run 10 runs, and the true velocity is 10. And what we observe is that in 9 out of the 10 cases, we converge to the true velocity. There is one run that does not converge. It converges to a suboptimal local minimum. But in 9 out of 10 cases, we're able to get a very accurate estimate of the velocity. So you can use both neural networks and Gaussian processes to solve these inverse problems. This one is a different kind of inverse problem. This one here, so we're going to apply a neural network, and this is a so-called hidden field inverse problem. So what you have here is the Navier-Stokes equation and the advection of a scalar, a passive scalar, a passive tracer that moves along the flow. And then, obviously, you have the system of PDEs, and you have four fields. You have the tracer concentration, you have the horizontal velocity, the vertical velocity, and the pressure. This is a two-dimensional flow problem. There is a cylinder. You see the cross-section of the cylinder, and the flow is moving from left to right. The only information you have is the inlet velocity. So what is the velocity of the flow coming in from the left? And you have some scattered concentration data, noisy concentration data. It's not a dense grid on the tracer concentration field. It's just some scattered concentration data. So here I'm going to use a neural network along with the Navier-Stokes equations and the advection equation to estimate the velocities and the pressure without having no information on the velocities or the pressure. Also, without having information on the boundary conditions, either on the walls or on the cylinder. So you don't know anything about the cylinder. In fact, you, believe it or not, you don't even know the position of the cylinder. So you don't know that. The only thing you have is the scattered concentration data and the equations and the inlet velocity. So here I'm showing you the solution, which is very accurate. So you're able to reproduce this turbulent flow using a neural network. This is a Reynolds number 100, which is not very high, but it's already high enough to produce, in fact, these vortices that you see downstream from the cylinder. This is a well-known problem in computational fluid dynamics. It's the famous flow around the cylinder, and of course, this is using the velocity and the pressure. You can compute forces on the obstacle on the cylinder. This could be an airfoil in aerospace engineering, etc. So this is, I think it's a very good example of using neural networks for inverse problems. There's no way you can use traditional numerical methods to solve a problem like this. I mean, it's just no way, okay? All right, the other possibility is the hard possibility. So here I just have one simple example here. So this is called the characteristic informed neural network. So for hyperbolic transport problems, you can use the characteristic method to, in fact, obtain a layer that enforces the PD. So in this particular case, it's a linear advection. It's very simple, but it can be more complex. Here, what you see is a layer that contains the velocities, and then the output of the neural network is guaranteed to be a solution, because in fact you transform to the characteristic space with the first layer, and then you do functional approximation of the characteristic space, which is guaranteed to satisfy the PD. So you just need to, of course, train the network on the initial data or boundary data, but the PD is already satisfied. So there is no loss, physics-informed loss. There's no physics-informed loss. There's only data fitting loss. So this is a regular neural network. It's trained on just data fitting, okay? No physics. So this prevents unphysical solutions and also prevents those imbalances between the different loss components. This is an example, and here we can see that the PINN starts degrading at velocity around 40, whereas the characteristics informed neural network can still predict well at velocity 40. At velocity 50, at least with this horizon of training, the characteristics informed neural network starts degrading. But at 40, it still produces a very accurate solution, whereas the PINN does not. So this is just an example of that. But so the idea is that even if your solution is wrong, it's still a solution of the PD, which doesn't help, I know. But the output solution is never unphysical. The output solution is never unphysical, right? So if you have any questions, I mean, you can ask or maybe hold until the end. That's okay. So next we'll talk about neural operators. So we only talk about data-driven neural operators. There is also physics-informed neural operators, but here we are just going to talk about data-driven neural operators. So the idea here is that you're solving a parametric PDE, which means that it's actually a family of PDEs, and the solutions corresponding to this range of parameters becomes a manifold. It's a solution manifold. And there is a solution operator that takes you from each parameter to its corresponding solution. You're interested in approximating the solution operator. Provided that the solution operator is continuous, you can approximate it arbitrarily well with a neural network. So the solution operator typically in a well-posed problem is continuous, okay? So for instance, you take the Darcy's equation, and the parameter here is a function, in fact. So this parameter can be a function. It's the porosity at each location. And then the solution is the fluid pressure at each location. So by learning the solution operator, given a new parameter field, given a new porosity profile, I can estimate the fluid pressure without any weight updates, no further training. So there is an initial training step, which can be time consuming, but once it's trained, I can make predictions very fast. So that's the idea. And of course, you can use neural networks to do this. You could use Gaussian processes in principle to do this. And of course, you can use more traditional scientific computation methods, including POD bases and things like that. Okay. So the idea then is that you have an infinite dimensional space for the parameter, and you have an infinite dimensional space for the solution. But you cannot deal with infinite dimensional objects on a digital computer. So what you're going to do is you're going to have to discretize these functions, okay? And once you have these pairs of parameter and solution discretized, in fact, pairs of parameter and solution, you can train your neural operator, and then the testing on a new discretized, again, parameter solution produces a discretized solution. So here is again the idea that the physics is in the data, okay? I mean, you might have an advantage here if you actually don't know the physics, or the physics you have is incorrect. If you try to use a physics-informed approach with incorrect physics, of course you're going to get an incorrect solution. So, but if you have a completely data-driven approach, you could then implicitly learn the physics through the data, with that caveat, that you might need infinite amounts of data. But for simple problems, you don't need infinite amounts of data, okay? I mean, if the problem is simple enough, you can have a reasonable amount of data that can solve that problem. So that's the idea. Now, this discretization introduces an issue, which is can we call a neural network an operator learner if it's learning the resolution. So it should not learn the resolution, because if it's learning the resolution, then it's a discrete operator. So it should be, in some sense, insensitive to the resolution. So here we see on the left UNet, which is very sensitive to the training resolution. If you train on 64 by 64 grids, you only get a good result if you test on 64 by 64 grids. Whereas on the right, you have a Fourier neural operator and a convolutional neural operator where it's much more flat. You can train on 64 by 64 and you can test on 96 by 96. But, you know, there's a limit, of course. You know, if the resolution is too small, you can't get a good result. But this is more or less the idea. So there is a big debate right now about, you know, are neural operators really neural operators? Is literally the title of this paper where I took this figure from. So are neural operators really neural operators? So that's the debate. From a practical point of view, if you're only testing on the same resolution that you train, you don't care, okay? I mean, you just don't care. I mean, if you are always testing on the same resolution that you train, no one cares, okay? But it's still a theoretical question, okay? All right, so our contribution in this arena, recently we have been working on dipole sets, which is a combination of dipole nets, which is a well-known neural operator, and deep sets. So here, what you can achieve with these deep sets encoder is first a variable number of samples. So your resolution, your training resolution, in fact, can vary. You know, you can use different resolutions for your training. And also introduces a permutation invariance bias, because these points, these samples from the parameter function, they are permutation invariant. I mean, it doesn't matter if you sample x1 first and x2 second, or vice versa. So the neural network doesn't have to learn that the problem is permutation invariant. Instead, you introduce an inductive bias of permutation invariance, which allows you to use less data. Okay, so that is the basic idea. Here you see some results. You know, for a simple nonlinear diffusion reaction PDE, the operator learning problem is to map from f of x, forcing function, to the solution. So here we are seeing, after training the network on a range of discretization range, we see the solutions for a new forcing function where you discretize on 5 points, 10 points, 20 points, and you see the prediction of the neural operator, and you see the exact. So obviously the error is decreasing. You can go for 50, 100. The error becomes very small. Indeed, you see here the error plotted, the L2, relative L2 error plotted as a function of the testing resolution, where the two vertical dashed lines is the range of training resolution. So with dipole sets, you can have a range. We can see that within the range, and in fact, on the right of the range, the error is flat. You know, it's small, 10 to the negative 3 to 10 to the negative 4, which is small, okay? And it's relatively flat. So it agrees with that idea of resolution invariance. Obviously, on the left, as the number of samples become very small, the error increases, okay? But, you know, I think these are promising initial results for this class of neural operators. Okay, the last part of the lecture, which I'll try to do as fast as I can, is yet again a new neural operator architecture that our postdoc Giza Chen is working on, and it's called Inv-CON. So it's a neural operator for time evolution problems, where modify a UNet to have as input the time along with the in this case two-dimensional fields, and also the parameters as inputs. So we call this the Inv-CON, and here we're going to apply this to a plasma physics problem, or plasma turbulence model, which is called the Hasegawa-Wakatani model. And the Hasegawa-Wakatani model is a very well-known benchmark for numerical methods for plasma turbulence. It's a two-dimensional problem, and it models different physical quantities: the plasma electrostatic potential, the electron density, and the electrostatic vorticity. So here we are using a traditional numerical code. It's called the HW2D to generate the data to train our neural operator. And you're seeing down here a sample of snapshots from the code after the turbulence phase has begun. So we discard the initial transient phase, and then we take only the turbulent phase. So we generated 320 evolutions with different choices of the parameters on 128 by 128 grid. That's the training grid, and the step size of 0.005. These are, of course, normalized time and space appropriately. So we do this for 40,000 time steps. We take 240 for the training set and 80 for the testing. And then you run the Inv-CON auto-regressively. So you start at the initial snapshot, you predict t plus delta t, and then you use t plus delta t as the input to predict t plus 2 delta t, and go on like this. So the network is trained, and then you give a new snapshot from the test data, and then we compare here the numerical code with the Inv-CON prediction. They agree very well until a certain time, and after that it starts diverging, the numerical code and the Inv-CON prediction. But obviously it's a chaotic system, so even minor deviation is going to grow, right? So you don't expect in fact that they're going to agree forever, but the agreement is very good. And also the important thing here is that the inference time for each snapshot is a fraction of a second, whereas obviously the code takes a long time, okay, to produce an evolution. So with this trained network, we can produce an evolution very fast, okay? The important thing for plasma, whether in astrophysics or in fusion, is the statistics of the evolution, not necessarily the fields themselves. So they are interested in things like the turbulent particle flux or the so-called primary sink. And here we are comparing this quantity. So we compute the evolution, and then we compute the quantities based on the evolution, and we compare them. So here we compare them with the numerical code, so-called truth here. What we observe is that the general frequency behavior is very close. I mean, so the frequency content is very close. Even if the time domain evolution does not match exactly because of the chaotic behavior, but the frequency content is very close. We also compute the mean and the standard deviation of the time evolution of these quantities, and they also match quite well. In fact, we do it between 300 and 600 in time, whereas we train only between 200 and 300. So that's another way of testing. We also compute the Fourier transform of this quantity squared, the magnitude squared of the vorticity here, which is typically used also as a benchmark. And we see here that we match the expected power law behavior of this quantity as a function of wave number. Finally, we can use this architecture for inverse problems. So here we are using some data, some evolution, but in fact we're using very small amounts of data. We are taking some pairs of t and t plus delta t randomly from the evolution. And then we are finding the parameters by gradient descent on the input of the trained neural network. So you don't retrain the neural network. The neural network is not retrained. It is actually only the inputs parameters which are modified by gradient descent. And we can see that in a relatively fast amount of time, 200 seconds, we are able to, in fact, get a good approximation. We can see the same thing here, where we repeated the procedure several times, and we plotted the scatter plot. And we can see that, obviously, as the amount of data increases from 2 pairs to 8 pairs and 32 pairs, the results improve. We can also see that kappa 0 is very easy to estimate. In fact, you only need 2 pairs to do a relatively good job. I mean, a very good job. And CPB is next, and the other two are more difficult to predict. But still, there's a strong signal here. I mean, there's a strong signal. So, so that is what I had about this. So just to finalize, then, a little ad here for our scientific machine learning lab. So we have been doing this for 5 years now. It is almost 5 years. It is the first lab, the first thematic lab of TAMIDS. So it was the pilot lab. And we have a research mission, education mission. There are seminars, workshops, demos. So you can go to the website and check this out. We have the seminar series where, in fact, Young-Soo was the speaker this past Monday. So you can see all this information there. So, I mean, that's it. So, now I think I hope I was quick enough in time, and we could answer questions.
Yeah, thanks for the wonderful talk, Ulisses. We have several questions in the chat room already, so I'm going to read them one by one.
Okay. Sure.
Connor asks, how does validating the learned operators compare to validating physics-based models solved with traditional numerical methods?
So the question is how you compare the results of the operator learning with the traditional numerical methods. Is that the question?
Yeah, I think so.
So well, you have traditional numerical methods for parametric PDs, but typically traditional numerical methods apply to single PD, right? Now with reduced order modeling, POD basis, etc., you can actually solve parametric PDs the same way that you solve with neural operators. It is very interesting, in fact, to compare these approaches. We have not, I'm not aware of any simulation study that does a very thorough comparison. We do have POD DPONets, which is a hybrid, sort of a hybrid, where you take the POD basis and you use as the trunk of the DPONet, and then you only train the branch of the DPONet. So they call it POD DPONet. So there are possibilities of hybridizing these approaches, in fact, and there are possibilities of comparing them. But I'm not aware of any systematic comparison, so maybe you guys can do it at Lawrence Livermore. But so
Sure.
Can I clarify the question? Sorry.
Yeah.
yes.
I'm wondering if there's strategies for training a neural operator on some set of data and then deploying it in practice where you don't necessarily have a guarantee that the operating conditions are going to be similar to the training data. It seems like people know how to address this issue for physics models because you don't worry about generalization. And I'm wondering if there's a strategy to, have some bounds that says your model's going to work in practice.
It's the same thing with any data-driven machine learning approach. If your test data does not correspond to your training data, then you're going to have a distribution shift or out of distribution problem. And of course, in all the simulations I showed, the testing data comes from the same place as the training data. But if that's not the case, then you're going to have to adopt some other strategies. It's exactly the same problem that you have in computer vision or natural language processing or any data-driven machine learning. You're right. If you have the physics-informed component, then, that alleviates this issue. But the physics component also can be incorrect. So, the physics component could be incorrect. And so there's really no way to get out of this except for sound experimental design. So, if you have sound experimental design, data collection, etc., you make sure that your test data is as close as possible to your training data. So that's the answer I can give.
Thanks.
Okay.
Okay. The next question is from Johannes. What training strategy do you use for learning the time-dependent operator in Inv-CON?
What training strategy? So this is it's traditional ADAM, optimization. It takes time. This is a big network, so it takes many hours of GPU. But the idea is that once it's trained, you can make very quick predictions. So you can predict the evolution. Yes.
Sorry, I meant more specifically if you're learning the operator for a single simulation time step or a user-defined time step, or if you're training over many different size time steps.
Yes. So the operator is trained to predict a given time in the future. So, the time is an input. So, given the initial snapshot, it can make predictions at any time in the future, in principle. But so it's totally flexible. But in the video I showed, we are using it autoregressively. So we are predicting, T0 plus delta T. Then we take T0 plus delta T to predict T0 plus 2 delta T. And when we use it autoregressively. But the operator can make a prediction of any time. Given the initial condition, can make a prediction at any time. It's only when you want to have an evolution that you need to do it autoregressively. So.
Okay, but the loss is just with adjacent.
The loss is just between the initial condition and the snapshot at time t. So you're going to train it on several times. You're going to train it on the entire evolution, in fact, but the loss is between the prediction at time t and the snapshot at time t. So,
okay, thank you.
Okay, yes.
So Elon asked a series of questions actually. So how long in time was the Hasegawa-Wakatani trained relatively to the near-point of exponents, and how far in time do the statistics agree for the model? And can we use timescales much longer than the near-point of time for this?
So as we saw, the up to 20 time steps, the evolution was agreed well. I mean, not necessarily the fields agree, but the statistics agree. I mean, the statistics agree over this horizon. If you increase the horizon, there might be less agreement. I don't have that data here, but yes, obviously, if you do a long rollout, you start accumulating more errors. But the frequency response is very close, and the mean and standard deviation also very close over this time interval. I'm not sure if that was the question, but
yeah, I mean, if I could just like kind of clarify, I mean, you said very correctly that what people ultimately are really interested in are things like fluxes and what what the mean is and what the standard deviation is. So, I guess what I'm wondering, I have like a couple of kind of related questions. One is, if you trained it for a very long time, would that help? But I assume the answer is not really, because in terms of like pointwise convergence, because of this butterfly effect that's happening. But then there's the more important question of how well do the statistics agree as we go further and further in time? Because it may very well be that you capture like dynamics on the attractor, and so then the statistics are great. And then there's kind of like, normally for these types of simulations, people use the ergodic theorem to collect statistics, and they'll tell you that
use what? I'm sorry.
The ergodic theorem.
Ergodic theorem.
To tell you that a time average gives you the average that you care about.
Right. Right.
Whereas here, I think you might actually have a lot of statistical information, and you don't even necessarily need to run your simulation for a long time. Like, you just already have statistical information about
right. That's a good point. Yes, that's a good point.
So it's sort of like, even if it agreed for short times, you may not need to run it for long times to tell me.
If it's ergodic, yes, I agree. If it's ergodic, then yeah, I mean, you can capture those statistics over a short window. Yes.
So that's what I'm trying to ask is, to what extent do you think maybe you need to look a little closer at the data, but like, to what extent are these things actually satisfied? This would be kind of exciting if you could.
Right. So thanks for the input. I mean, this is a work in progress. So I'm showing you some very recent results. So it's a work in progress. We have collaborators in the Institute of Fusion Sciences at UT Austin, and they are helping us with the physics of the problem. And but this is yes, I mean, this is a good question. I mean, I'll take this question to our collaborators. This is not a finished work. It's not a finished job. So the preprint hopefully will be out at some point soon, but it's still work in progress. So I'll be happy to share the preprint with all of you when it's ready. So.
Okay. Sounds good. I think these are all the questions. I hope I didn't miss anyone. And I guess we can call it a fruitful discussion. Let's thank Ulisses for sharing his excellent research with us today. I will stop.
It's my pleasure. It's my pleasure. Yes. Thank you.